Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to provide another impulse momentum example. So let's see, number 20, chapter 15. The 5 kilogram block shown hits the stand and is stopped in 0.9 seconds. The block does not rebound. Find the average force applied from the sand onto the block. Okay, so the key here that you want to use momentum methods is that we're talking about forces and times. So work energy methods are about forces and distances, but impulse momentum methods are about forces and times. So let's go ahead and take a look at this. So let's see, this thing starts here at 2 meters per second. We're probably going to want the velocity right before impact here. So let's call this position 1. Here's position 2. There's a velocity downward. Let's call that V2. Now you notice there's some daylight right there. And again, that's deliberate. This is supposed to be an instant before impact. All right. And as I mentioned a little earlier, all right, momentum methods is about force, velocities, and times. But energy methods are about force, velocities, and distances. So what we're going to want to do here is apply work energy between 1 and 2. So I'll go ahead and do that. Potential energy 1 plus kinetic energy 1 plus any work done from 1 to 2 equals potential energy 2 plus kinetic energy 2. Putting a datum at the ground right here, this is going to be mgh plus 1/2 mv1 squared, because this thing is moving at position 1, plus 0. If we throw out air drag, there are no non-conservative forces acting between 1 and 2. PE2 is 0 because we're at the datum. KE2 is 1/2 mv2 squared. Now, I don't have a calculator on me. I'm going to let you folks work this out. It's a almost trivial calculation here. The masses divide out. You go ahead and put in, 9.8 meter per second, 8 meters, 2 meter per second. Don't forget to square it. Solve that for V2, and you're going to get some number out of that, no doubt. All right, now having that number, now let's chat about the impulse momentum part of the problem here. So my third picture, block is just basically sitting on the sand. It has no momentum. All right, and the reason is that between 1 and 2, right, there's an impulse interaction between the block and the sand. All right, so if we draw the impulse diagrams, I'll put that right here. Now again, this is what's happening over this 9/10 of a second here. And there's really two forces here to consider. The gravitational force is still down. So we got an mg delta t down. And there's basically a normal force between the sand and the block, and that force is up. We'll call that an n delta t. And that's pretty well it. Now, a lot of times forces like this just won't be relevant here, but I think here we better put that in here. Now, what do I mean by not relevant here? If we're talking about like firing a bullet out of a barrel, the weight of the bullet is not a significant force here. But that 50 kilogram block, that's a 50 Newton force, give or take. Oh, I'm sorry, 5 kilogram block means that's a 50 kilogram force, give or take. That may be a reasonable force compared to this normal. So when in doubt, include it. Okay, now we just apply momentum concepts. So momentum, y direction. Now it does not matter which way we call up positive. In fact, I'll go ahead and write it both ways. Let's say we call up positive, but over here I'm going to do same equation, momentum y direction with down positive. You don't have to do both in a problem. I'm just going to do this to kind of demonstrate what it would look like. So with up positive, whoops, and one little glitch here too. This velocity here was for the work energy equation. Just keep in mind that when we write this, this needs to be a momentum vector. So with up positive, this is minus mv2. Okay. Now, plus our impulse, which is going to be n delta t in the positive direction and mg delta t in the negative direction, or downward. And then, third picture, that's going to be an equals 0, because there's no momentum in picture 3. And now what we'll do is just solve this algebraically for the normal, and you're going to get some number out of that. Now if we go ahead and write the same equation with down positive, right, this vector is now in the downward direction, so this is going to be mv2. Okay, the mg delta t is now in the positive direction, so we'll put plus mg delta t. The normal, all right, that impulse is now in the other direction, so minus n delta t. All right, and now in picture 3 we have no momentum, so equals 0. And you would solve this for the normal. And you're going to get the same value, even the same sign out of this, okay? You'll notice by inspection here, if you look at this, you're going to get a positive number for the normal. So the positive number doesn't mean up. What it means is it's in the correct direction in your picture. And when you solve this one for the normal, you will also get a positive value. So again, it doesn't matter which way you write your momentum equation, as far as which way you define the direction. I hope that this helps demonstrate how to draw impulse momentum diagrams and use them to write equations. Have a great day.